Hi, my name is Shahnawaz. In this lecture, we will prove the Brouwer fixed point theorem for unit basic. But before that, we will prove a result regarding the vector fields of B2. So we have this theorem here. So given a non-vanishing vector field of B2, where B2 is a unit disk, there exists a point x. There is a point of S1 where the vector field point is directly inward, and a point of S1 where it directly points outward. Now, before proving this theorem, we just want to recall here what do we mean by a vector field. So actually a vector field is an ordered pair x vx, where x is some point in Rn and v is a function from Rn to Rn. Now what it does, it is actually a way of visualizing functions that have same number of dimensions in their input as in their output. For example, if we look at the function, say v from R2 to R2, given by, say, v of xy is y I hat minus x j hat, where I and j are the unit vectors along the x-axis and y-axis. So if I look at certain points, say suppose this is our coordinate system and this is the point 0. So if I look at the point v of 0 0, we get the point 0 0. So that means this is a point 0 0 comma, so let us call this point x here, this point vx here. So this is the point x vx. So actually it is not possible to draw a graph of a such function, because it needs 4 dimensions to visualize this graph. So to get a picture of how this graph will look like, we use this vector field. So at this point is when we give input 0 0, we get output 0 0. So we can represent this point by this vector by this point over here. So if I give the input, say v of 1 comma 0, we get the vector 0 minus 1. So this is the point 1 0, and this is the point 1 0 over here. Here we get the point 0 minus 1 here. That means from here we have to draw an arrow, draw a vector towards this point 0 minus. So this point over here, this represents the point. So if this is x1 here, this is vx1. So this is the point x1 vx1. Similarly, if I give the input say v of 1 1, we get the point 1 comma minus 1. So 1 comma 1 is a point over here. So we get a point in the direction of 1 minus 1. So this is a point over here. So if this is x2, this is vx2, we get this arrow. Similarly, if I give this input here, I get an arrow like this. Similarly, and a point over here will give like arrow this, a point over here will give like arrow this. So this this moves in circles. So this gives a picture of the graph of this function. So let us prove this now. Now non-vanishing here means, so this vector field, this vanishes at the point 0 0, because at 0 0 we get the output 0 0. So this is the vanishing field. But in case of non-vanishing fields, we have a vector field which does not vanish, which does not assume the vector 0. So let us prove this. So a vector field on B2 is an ordered pair, x vx, where x is some point in B2 and v is a function B2, v is a function from B2 to R2 and is a continuous map. So we say v point is directly inward or outward at a point. We say v point is directly inward or outward at a point of x in S1 if v of x is ax. V of x is ax, where a is less than 0 or a is bigger than 0 respectively. So if v of x is a negative scalar times x, we say the vector field point is directly inward at x. Otherwise, if a is positive, we say the vector field point is directly outward at point x. Also, since the vector field is non-vanishing, since the vector field v is non-vanishing, we can think of the map, therefore this v of x is nowhere 0, and hence we can be think of as a map from B2 to the punctured plane R2 minus 0. Now we have to prove there is a point on S1. We have to prove there is a point of S1 where the vector field point is directly inward. So we assume otherwise. So assume on contrary that there is no point on x on S1 where the vector fields while the vector field point is directly inward. So assume on contrary there exists no point I mean, let us assume that v of x is not equal to ax for any x in S1 while a is negative. So assume vx is not equal to ax where a is negative for any x in x. So let us see what will happen. So what we do, we take w to be the restriction map of b2 on the S1. So we have this v, a map from this b2 to the puncture plane. So here we have a puncture, sorry, so this is the puncture over here. So this is our plane. So this is our map v. Now we can define another one more map w, which is actually the restriction of v to S1. So this is the boundary of b2, which is S1. So this S1 is a map from this w is a map from S1 to the puncture plane. So let w from S1 to puncture plane R2 minus 0 be the restriction of v onto S1, that is this w is v restricted over S1. So since we can extend this w to the map v, we get then w is null homotopic, because this is what we had done in the previous lecture. So since w can be extended continuously to v from b2 to r2 minus 0, we note that this w is null homotopic, i.e. the map w is homotopic to a constant map. So now we can we have an injection, the inclusion map of S1 into the puncture plane. So let us call that map J. So let J be an inclusion map of the inclusion of S1 into this plane, the puncture plane. So this be the inclusion map. Now one can note here this R2 minus 0, the plane, and this plane over here, this is a retraction of S1. So since R, which is a map from R2 minus origin to S1, given as R takes the point x to x mod x divided by norm x. So this is a retraction of the punctured plane onto S1. So therefore the homomorphism induced by this inclusion map over here is injective. Therefore the induced map J star, which is a map between the fundamental group of S1 and the fundamental group of R2 minus 0. So one can note here this R2 minus 0 is a retract of S1. So this J star is a map between these two groups. So one can note here this J star is injective. So hence non-trivial. So that means this J cannot be null homotopic. So the induced map J star induced by J is injective, and hence is non-trivial. Therefore this map J over here, this is not non-homotopic. Now let us define a map. So define a map, say F from S1 cross the interval 0 1 to the punctured plane R2 minus 0 by f of xt is tx plus 1 minus t times w of x. So this is true for all x in S1 and t in the interval 0 1. So clearly f is a continuous map. So f being linear, so it is a continuous map. So now one can note here, so now f of so we wish to prove we wish to prove this homotopy map is this map f of xt is non-zero. So for t is equal to 0 or t is equal to 1, we have, so f of x 0 is actually w of x, and w of x being the restriction of a non-vanishing vector field, so it also does not vanish. So this is for all x in the circle. So the reason is that since w x is a restriction of a non-vanishing vector field. Also, if we take t to be 1, so f of x1 is just x, which is same as j of x, which is also not 0 for all x in S1. So hence f of xt is non-zero at t is equal to 0 and 1. Now let us check what will happen to f when we choose this t to be a point between 0 and 1. So let t be a point between 0 and 1, and suppose f of xt is 0. So if f of xt is 0, it means this expression over here, this is 0. So that is tx, that is tx plus 1 minus t times w of x is 0. So this gives w of x is minus t over 1 minus t times x. Now one can note here this quantity over here, this is positive, this t is also positive, so this scalar over here minus t over 1 minus t is positive, negative. So that means w of x point is directly inward. So that is not the case, because we just have assumed at the first place that there is no point where the vector field point is directly inward. So this is our assumption. So v of x cannot be equal to a of x where a is less than 0. So this is not the case by hypothesis, by our assumption. So hence this is non-zero. So if this is, if this f of xt is non-zero, then this f gives a homotopy between the inclusion map and w. So hence f is a homotopy between the maps J and W. Now because when we restrict f to 0 we get W, when we restrict f to 1 we get the map J. So but W is null homotopic, this implies J is null homotopic, but we have proved here that J cannot be null homotopic, hence our assumption is wrong. So this shows that J is homotopic to W, but W is non-homotopic. W is homotopic to a constant map. Hence by transitivity, J is homotopic to a constant map. In other words, J is non-homotopic, but that is not the case. But W is non-homotopic. Hence, J is null homotopic. J is null homotopic, which is a contradiction. Hence our assumption is wrong. That means there is a point x of S1 where the vector field point is directly inwards. Now to prove there is a point on S1 where the vector field point is directly outward, we just we just prove the same result for the vector field x minus vx. So now to prove v points directly outward at a point of S1, we apply the above result, we apply the above procedure to the vector field x minus vx, and we will get what we require. Now let us prove the Brouwer fixed point theorem. So Brouwer fixed point theorem. So this is for unit disk. So what it states, so it states that if f is a continuous map from the unit disk to unit disk, then there exists a point x in B2 which remains fixed under this map, such that f of x is equal to x. So let us prove this. So we proceed by contradiction. Suppose that no point remains fixed. Suppose that f of x is not equal to x for any point x in the ball B2. So if this is the case, then the function Vx given by f of x minus x gives a non-vanishing vector field. This is a non, so this gives a non-vanishing vector field. Let us call this vector field x Vx on B2, and therefore by above theorem there exists a point x of S1 where the vector field point is directly outward. So therefore there exists a point x of S1 where the vector field point is directly outward. That is V of x will be equal to a times x, where a is bigger than 0 and where a is bigger than 0. But this is same as f of x minus x gives ax. So this implies f of x is same as 1 plus a times x. Now one can note here f is a map from B2 to B2. So if we look at the norm of this vector, it is bigger than 1. So it lies outside B2, which is not the case. So this gives a contradiction, since 1 plus a times x lies outside the unit ball, lies outside the unit disk. B2. So this proves the Brouwer fixed point theorem. Now let us do a small application of this result. So let A be a 3 cross 3 matrix of positive real numbers. I mean, every entry in A is positive as well as real. So then we claim this A has a positive real eigenvalue. So then A has a positive real eigenvalue. So let us prove this. So let T from R3 to R3 be a linear transformation whose matrix relative to the standard basis for R3 is A. So let T from R3 to R3 be a linear transformation whose matrix relative to the standard basis of R3 is A. Now let us consider B to be the set which this is the hollow sphere S2. Let us take its intersection with the first octant, the set of all points in R3 such that, so these are the set of all points in R3 such that xi is bigger or equal to 0 for all I equal to 1, 2, 3. So actually this B is like this. So we have a sphere here, so it goes like this. And we have a sphere here. So this is our sphere. And this B is this portion over here. So let us pick a different color here. So this B is this portion over here. So this is part of the unit ball S2. So this is the intersection of S2 with the first octant. So it is easy to, so this is over B. So one can note here this B is homeomorphic to the unit disk. So one can define a homeomorphism from this two-dimensional object to this two-dimensional object, because this B is a two-dimensional object. So one can note here the homotopy groups are of both the surfaces is 0, because the trivial group, the group 0. So they are homeomorphic. So clearly B2 is homeomorphic to a unit disk. So that means the Brouwer's fixed point theorem holds for continuous maps of B into itself. So the fixed point theorem holds for continuous maps of B into itself. That is, if we define a map from this surface to itself, which is a continuous map, then that map has definitely a fixed point. So one can note here. So now if x is a point like this, x1, x2, x3 in B2, so one can note here this point is in B2, so that means all the coordinates are non-negative and at least one of them is positive. So these 3 pointers, these 3 points are the only 3 pointers where certain coordinates are 0, but any of these coordinates have any of these points have at least one coordinate 0. So if we choose any point except these 3 points on this B, so that B is going to have all 3 coordinates positive positive. So now if B is in if this X is a point in B, this is not B2, this is just B here, excuse me. So this is B, then all the components of X are non-negative. And at least one is positive. Now our matrix A is given to be a real matrix with all entries positive real numbers. That means if we look at the vector Tx, so this will be a vector whose all coordinates are positive. So since A has all positive entries, therefore Tx is a vector whose all coordinates are so this is a vector whose all components are positive. Now define phi from B to B by, so this phi takes an element, so this phi takes an element y in B and it maps it to the element y mod norm of y. So clearly phi is a continuous map. So this is a continuous map, and hence there exists a point So there exists a point x naught in B which remains fixed such that phi of x is x. Phi of x naught is x naught. So this gives x naught is t of x naught norm t of x naught, or t of x naught is same as norm of t of x naught times x naught. So this means that a of x naught is, let us call this lambda over here. So this is lambda of x naught. That means lambda is an eigenvalue corresponding to the vector x naught. So hence T has a positive eigenvalue, namely norm of t of x naught. Now why this is positive? Because every component of the vector t of x naught is positive, so therefore this norm will be a positive real number. So this proves the result.